So our final unit starts with something old and then expands on that into something new, which is kind of our jumping off point for the remaining part of the unit. And so we're going to go back to our rational functions, which we had graphed earlier in the year. So we've got kind of the same slide that we had looked at that time that kind of helps us with the sketching of those graphs. So if we'll recall, a rational function is a ratio of two polynomials. The big restriction is we have to make sure that we have an x in the denominator. We may or may not end up with an x in the numerator, but we certainly have to have an x in the denominator. And so when we studied these, we saw that these functions can have vertical and horizontal asymptotes. There were also slant asymptotes, but we're going to ignore those types of functions for now and just focus on those that have horizontal and vertical asymptotes. And so hopefully we remember that the vertical asymptotes of a rational function occur when the denominator equals 0. So those were our vertical brick walls that our graph could not cross because those were values of x that we could not plug into our function. The rule for horizontal asymptotes was a little bit different though. The reason behind horizontal asymptotes was that was the long-term trend in the graph. So as we extended farther and farther to the left or to the right, this was the output that the function was approaching. And so what we found was if the denominator had the higher degree, had the higher exponent of x than the numerator, then the graph would eventually trend to y equals 0 as an output, the farther out to the left and right we would go, because the denominator would grow faster than the numerator, and that would be true in both of the examples that we see up above. And then if we had the same highest exponent in both the numerator and denominator, then the numerator and denominator trending together in terms of how fast they're increasing in size. And so then as a result, it was the ratio of the leading coefficients served as that output that our function was approaching. And then of course we could have x and y intercepts, and those are often features of graphs that we're interested in. So the x-intercept, of course, is when the output of the function is 0, meaning that the numerator would have to be 0, because 0 divided by anything is 0. So we can just set the numerator equal to 0 to find any x-intercepts. And then the y-intercept of a graph is when the input is 0. So if we're on the y-axis, that means the x-coordinate is 0. So if we just plug in 0 for x into our function, that will tell us what the y-intercept is. So we just plug in 0 for x. So again, these are all things that we had talked about at the time that we first looked at these functions, but I wanted to review these ideas a little bit before we get into graphing a couple of these. So we're going to apply the guidance for all of those features to the examples that we see here. So we'll start off with a nice simple one, f of x equals 1 over x plus 4. So to find the vertical asymptotes, we've got to set the denominator equal to 0 so we can find what values of x we can't plug into this function. And so hopefully easily enough we can see that x equals -4 is that location. So I'm going to put in a vertical dotted line there at -4. For the horizontal asymptote, the rule is to determine where the higher exponent of x is. In this case it's in the denominator, which means that our graph, as we go farther and farther out to the right or to the left, is going to trend towards the x-axis, towards an output of 0. So the x-axis, y equals 0, is our horizontal asymptote. For the x-intercepts, if you look on the slide previously, we're supposed to set the numerator equal to 0, so that's what generates an output of 0. But in this case we can't because there's no variable up top. So that means there is no x-intercept, so we never cross through the x-axis. That's important knowledge for us. And then for the y-intercept, we just plug in 0 for x, so we get 1/4 as that value, 1 over 0 plus 4. So just a little bit above the x-axis there, I've got that location. And so then when we tried to graph these, finish off the graph of these functions previously, we're really just trying to get a ballpark idea and understanding how the graph relates to these features that we found. So for the right-hand side of the graph, to the right of that vertical asymptote, we really already have all the information that we need. So I know my graph is going to approach 0 as an output the farther to the right I go. So we're just getting closer and closer to the x-axis. It definitely does not curl up or anything like that, so we want to make sure that we don't do that. And then as we get closer and closer to that vertical asymptote, as our graph moves to the left, recall that there's only one of two ways that the graph can go. It's either going to shoot up to positive infinity or go down to negative infinity. It can't cross through that line. It's got to go either up or down. And because we know that there are no x-intercepts, the graph never crosses through the x-axis, the only thing this graph can do is take off and go up. And so we could verify that with a few more points if we wanted to plug those in, but I'll leave that to you. Then we just have to figure out what's going on the other side of that vertical asymptote, and so I just need to plug in a number on that side. So if I go to the left of that vertical asymptote, we can plug in -5. So if I plug in -5 into the function, 1 over -5 plus 4, we get -1 as the output. So that means my graph goes through that location right there. And again, that tells me everything that I need to know for what's happening on that side. As I approach the vertical asymptote, now my graph is trapped in this lower left-hand corner. So it must be shooting down to negative infinity. But then if I go to the left, the farther out that way I go, I know that my long-term trend is to approach that horizontal asymptote of y equals 0. So we're headed that way. Again, not bending away from the asymptote there, but getting closer and closer to it the farther we go. For the second example, we can see we have a little bit more going on, but our approach is still going to be the same. To find the vertical asymptotes, we're going to set the denominator equal to 0. Hopefully either by factoring or by using square roots. We recognize that we're not just going to have one vertical asymptote, but we're going to have two, one at +3 and one at -3. And so that means that we've got not 2 but 3 separate branches to our graph. The horizontal asymptote is again going to be y equals 0 because once again we've got the denominator with the higher exponent of x than the numerator. So even though we do have an x in the numerator this time, with the denominator having the higher exponent, it's going to get larger faster as we plug in larger positive and negative values of x. So our graph is going to trend to y equals 0. This time we will have an x-intercept. And so if I set the numerator equal to 0, we just get x equals 0. So we're going to be going through the origin there. And then the y-intercept is the result of plugging in 0 for x. And so 0 over 0 minus 9 is, of course, also 0. We can see that we've identified that location with one effort there. So recall that we can cross through horizontal asymptotes. We saw this before. But that will only happen in the middle area of the graph, not to the far left and the far right, since that's the long-term trend that our graph is approaching. So again, plot some points to generate the graph. If we go to the far right-hand side, so plug in something like 4. So if I find what f of 4 is, I don't even care what the exact value is. I just want to know if it's positive or negative so I know where my branch of the graph is located. And so we're going to be 4 over 4 squared minus 9. I can see that I'm going to end up with a positive value there. So I know that this part of the graph looks roughly like this. If I go to the far left-hand side, so I can plug in -4 so that I'm to the left of that vertical asymptote. So if I plug in -4, I'm going to have -4 over -4 squared minus 9. So this time I'm going to end up with a negative value, since I'm going to have a negative on the top, but a positive on the bottom. So I'm going to have a branch that's going to be down here. And then I just have to figure out what's going on in the middle. So I know that we've got that point at the origin, but I'm not sure if that's just a value that we bump off of, or if we're going to have an S-curve that's going to go through it. So I need a little bit more information. So if I plug in 1 for x, I can figure out what's going on to the right of that location, that the origin. So if we plug in 1, we get 1 over 1 squared minus 9. So we can see that's going to end up being a negative. So that means my graph is moving this way, and then there's only one way that it can go, since we have no more x-intercepts for us to be able to shoot up. the graph must be taking off and going down. And then if we plug in -1, just to figure out what's going on the other side of the origin, if we plug in -1 for x, we get -1 over -1 squared minus 9. Well, this we can see is going to be a negative divided by a negative, which is going to equal a positive, which means my graph must be going up. So we have an S-curve in that middle part of the graph. So again, these are rational functions that have these types of discontinuities, these asymptotes, these breaks in the graph that cause these anomalies to occur, these wild swings in direction of the graph in one direction or another, all of which we studied previously.